In this lesson, we shall focus on calculus, also limits, continuity, derivatives, and a rest of the things that pertain the mean value theorem and also Rolle's theorem. Yes, very, very important theorems. Right, we need to verify that the function satisfies the hypothesis of the mean value theorem on the given interval, then find all members C that satisfy the conclusion of the mean value theorem. Yesterday, we discussed the two hypotheses of the mean value theorem, and the two hypotheses of the mean value theorem have been stated here. Let us take a look at the two hypotheses of the mean value theorem so that you're able to remember them. Here is the mean value theorem. We said let f be a function that satisfies the following hypothesis. Hypothesis number one, f is continuous on the closed interval AB. F is differentiable on the open interval AB. Number C in the open interval AB, such that f prime of C is equal to f of B minus f of A, all divided by B minus A, or equivalently, you can just cross multiply and write it in this form. So now we're going to apply this theorem today, and as we apply this theorem, a couple of things are very important to us. What are the important things? They are the hypotheses, the fact that the function must satisfy the hypothesis of continuity on the closed interval and differentiability on the open interval. Okay, so and then we find the numbers in the open interval. So let's get started right now. Okay, let's solve these particular problems. All right, to solve number 15, so we shall start first with number 15. Actually, obviously hinted, number 15 is our very important example yesterday. Obviously, we record our time is approximately 16:30, meaning that we shall proceed to exactly 17:30 today afternoon. We actually have 1 hour of time to spare there. Okay, right. So what then exactly do we need here? We take note of the fact that if we check, is this function continuous? So in number 15, we ask the question, is f continuous? Right, is f continuous on the closed interval? Right, is it continuous on the closed interval 0, 2? That is the question. Obviously, because if you look at this particular function, it is a polynomial. So f is a polynomial, right? Is a polynomial function. Because it is a polynomial function, f is a polynomial function, which implies continuity, right? Which implies continuity over the interval 0, 2. Over the interval 0, 2. So, right, something that is very important, so take note of that. Over the interval 0, 2 there. Next, is the function f itself differentiable over this particular interval? Right, we investigate this function here. This is f is a polynomial, so f is a polynomial function, which implies that it is differentiable. Right, it is differentiable. So all polynomials are differentiable over open intervals, and in this case, between 0 and 2. What would then be the numbers we want here? Okay, so we proceed to check on that part together. Right, so what exactly do we need here? What we need is to consider f prime. Right, so we have to consider f prime of C, which is f of B minus f of A, all divided by B minus A. Right, pay attention to what happens here. Right, so at this point, we want to then find all numbers C. What are the numbers C? It's prime of C, which equals f of 2 minus f of 0, all divided by 2 minus 0. Right, so what then exactly is this? What is f primed of x? 4x minus 3, which is the same as what? Which is the same as 4c minus 3, which is equal to f of 2. Right, f of 2 is going to be what we can get here. So f of 2, it's 2 squared minus 3 times 2 plus 1. And this is the same as what exactly? Okay, want to find the value of this function at 2. And it is 2 by 4 minus 6 plus 1, which is exactly the same as 8 minus 6, which is 2 plus 1, which is 3. Right, so here you're going to put what here? You're going to put 3 there minus f of 0. F of 0 is going to be 0, 0, and f of 0 is going to be clearly a 1. So in other words, in number 15, we can see that f of 0 equals a 1. Right, so f of 2, yeah, we're doing the two, f of 0 and f of 2. F of 0 itself, it's a 1, right? So that is what actually we have here, right? So we say f of 0 is a 1. We divide by 2 minus 0. What is 2 minus 0? Right, so we can see that 2 minus 0, it becomes exactly a 2. The implication then is that 4c minus 3 is 2 over 2 becomes a 1. And with this, then it means that 4c is equal to 4. And if 4c equals 4, then c is 4 over 4, and c becomes 1. This is the conclusion. So we are to then find the the number c. Right, find all numbers c that satisfy the conclusion of the mean value theorem. So we actually can see here that the numbers c themselves are exactly 1. They are exactly 1 there. So c is 1. We have solved this one and we're done. We're through. Okay, we're excited. Let us try the next problem. The next problem is number 16. Right, so number 16 is exactly this one here. Let us first find the derivative of this. Why? Because we remember that f primed of c must be f of b minus f of a, all divided by b minus a. What is the derivative of this? Right, and obviously we know that the derivative of the polynomial function is actually 3x squared minus 3. This is the derivative of this function here. Okay, now we note that the value of the function at the extreme points of the interval, we find first f of 2, right, in which case it will be 2 cubed minus 3 times 2 plus 2. And this is exactly f of 2 equals 2 cubed, it becomes 8. Right, minus 3 by 2 is a 6. Plus 2, which is f of 2 equals, what is 8 minus 6? It's exactly a 2 plus 2, giving us a 4. Focusing on number 16, we have evaluated the value of the function f at one of the end points of the interval. The next step is to evaluate the function f at the other end point, -2 of the closed interval, which means we'll have f of minus 2. We plug into the function, which is minus 2 cubed minus 3 times minus 2 plus 2. And with this, we have exactly minus 8 plus 6 plus 2. And therefore, we have here f of minus 2. And what is this? This is exactly a 0 because 6 plus 2 gives us 8. And 8 minus 8 is 0. Okay, we're good. What is the derivative next? Because we want to find f primed of c, right? So which means that f of x, which is exactly x cubed minus 3x plus 2, which means therefore we have f primed of x, which is exactly 3x squared minus 3. All right, so now we evaluate, we actually now determine f primed of c in this particular expression. Remember, we are dealing with the mean value theorem. So, which means that we would have 3c squared minus 3 equals, what is f of b, which is, in this case, which is going to be exactly f of these endpoints here, which is going to be f of 2 minus f of -2. So it becomes f of the rightmost endpoint minus f of the leftmost endpoint, we divide by the same difference of the b minus a, if this is f of b minus f of a, and this gives us exactly this here, like so. And what then are we able to achieve here? This is 3c squared minus 3 equals, what is f of 2? F of 2 equals 4 minus f of minus 2 becomes a 0. We divide by this here, which is 2 plus 2, giving us a 4. And this is 3c squared minus 3 equals a 1. Okay, we're good. 3c squared equals. Now we have the number 1. We transpose the 3, making it positive, giving us exactly 4. Okay, at this point, we perform division on both sides of the equal sign, getting c squared equals 4 out of 3. And what is this? Right, we're able to see that this is plus or minus. The square root of 4 is 2. The square root of 3 becomes exactly the square root of 3. Now, these are the numbers C, but now you need to check these numbers. You need to check these numbers. Do these numbers lie in the interval here? Okay, like in the first case, we got the number C equals 1, and the number C equals 1 must lie in this interval. Let's check the hypothesis here, or the conclusion of the mean value theorem. Right, so if the two hypotheses of the continuity of f over the closed interval, the differentiability of f over the open interval, if these two conditions hold, or these two hypotheses are satisfied, then there is a number C in the open interval. So the number C lies in the open interval, and if that is true, then it means the instantaneous derivative equals the average gradient of the function f. So the number C must lie in the open interval. Okay, I'm just discussing this because we shall be looking at curve sketching very shortly. So as a consequence right now, we need to check if these numbers lie in this interval. So to investigate that, we will say, we can see that C is plus or minus 2 divided by the square root of 3. Right, which is exactly plus or minus. Now, what is 2 divided by plus or minus the square root of 3? We check that part. Okay, we check exactly that notion, the division part of this. What is exactly 2 divided by the square root of 3? Okay, we investigate that part. 2 divided by the square root of 3. You can always do that one. I'm just checking it quickly here. If you divide 2 by the square root of 3, whatever you're getting is actually plus or minus 1,15470. Okay, plus or minus 154. Is it here? Yes, it is here. Because if you check very carefully between minus 2 and 2, this number is there. And we agree that both of these numbers are actually members of the of this interval here. But as stated in the conclusion of the theorem, they are both members of the open interval. We just need the open interval. That's all. That is all. Okay, so this is very important. Now we continue and try. Okay, now we're leaving this one as a homework, and I'm giving you this one as a homework. We can always get back to them with time. So in other words, this one is your home activity, and this one is also your home activity. We've done 2, and we can always be in a position to get back to this one if time allows. But I want us to spend time on other things as well, because in the end, it's not only just about the mean value theorem, but there are other things. There's something very, very important, something extremely important, called the theorem by Rolle. Right, Rolle's theorem. Rolle's theorem is at the heart of operations in calculus and curves and graphs. And right, we cannot leave this outside our discussion. Let us take a moment to look at Rolle's theorem, a very important theorem that is applied in calculus. To arrive at the mean value theorem, we first need the following result. We take note of the following fact, that indeed Rolle's theorem has the tendency to actually be a prelude to the mean value theorem, to sort of be done before the mean value theorem. So the tendency is to say, to arrive at the mean value theorem, we first need the following result. So before we get to the mean value theorem, we need a result, and this result is called Rolle's theorem. All right, let f be a function that satisfies the following 3 hypotheses. What is the first hypothesis of Rolle's theorem? F is continuous on the closed interval. Okay, now this sounds interesting because you remember when you did the mean value theorem, we discussed the continuity of the function on the closed interval. This was the first hypothesis of the mean value theorem. We just decided to do the mean value theorem first. Second, F is differentiable on the open interval. Also, this one here is the second condition of our old friend, the mean value theorem. Third point, f of A equals f of B. Yes, f of A equals f of B. What is the meaning of this? Then, if this hypothesis holds and are satisfied, then there is a number C in the open interval. Like in the case of the mean value, this number C exists. So then there is a number C in the open interval such that f prime of C is equal to 0. What is this? This is a very interesting result. Now, this result here, we shall look at its applications, but it is telling us something very profound. It is saying here is a function, and we can draw a rough graph, a rough sketch of this function. This function here is a very interesting one. Suppose you have a function that does this kind of stuff. This is A, and that is B. And this is the y-axis, and this remains the x-axis. Okay, now, what do you then say? We say that if it happens that this function has intercepts at A and B, and f of A equals f of B, because here f of A is equal to f of B. At this point, what are the y values here? Here y is 0, which means that f of A is 0, and here it would mean f of B is 0. Just one case where this function here is having x-intercepts at A and B. Okay, then there is a number C in the open interval, so the derivative. So now, in other words, this is saying that if a function has x-intercepts and cuts the x-axis, for example, at two distinct points, then there's something we can say. We can say this function has a turning point, so that f prime of C is identically 0. This is Rolle's theorem. Now, take this into account. So it says that here is a function. It need not cut the x-axis, but here is a function that is such that f of A equals f of B. And if this happens, this theorem says this function must turn somewhere. This function must have a turning point. At the turning point, the derivative of the function is 0. Okay, this is an obvious theorem. You can say, even from school, this is one result that you think, okay, but even from school, why didn't even they teach this? Because it's very basic. Of course, we know turning points from school. At the turning point, the derivative is 0. That is why turning points are said to be stationary points. Why stationary? Because the functions are not increasing or decreasing. They are stationary. So now any tangent drawn to the curve will be a horizontal tangent. Okay, yeah, just a recap on this one. Let us just solve a couple of problems here, and then we shall give you some homework to try. Verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval. Then find all numbers C that satisfy the conclusion of Rolle's theorem. Okay, let's look at the first one. We need to rather verify that this function satisfies the three hypotheses of Rolle's theorem. What is the first one? The first one is that of continuity. So 2x squared minus 4x plus 5, this function, so f is continuous. Why? Right, so f is clearly continuous as a polynomial. Right, so f is clearly continuous as a polynomial over the interval. What interval is this? Over the interval -1, 3. Remember, continuity is over the closed interval. Moreover, f is differentiable. Why? Because the derivative of this polynomial, you can find so many derivatives there. So at this point, f is differentiable. Right, f is differentiable as a polynomial. All polynomials are differentiable. It's differentiable as a polynomial over the interval. Remember that differentiability is over the open interval. You just put round parentheses there. Okay, we're good. Next, what is then all this stuff here? Okay, what is then the third condition of Rolle's theorem. Right, the third condition of Rolle's theorem is this particular condition that f of A must be equal to f of B. So in other words, we're going to check here, we are doing number 9, we're going to check f of minus 1. It must be equal to f of 3, which is exactly minus 1 squared minus 4 plus 5, which is exactly 2 plus 4 plus 5. Okay, let us check exactly what happens here. And this here is 2 plus exactly 2 plus 4, which is a 6. You add 5, you have 11. And then we have f of 3. Check. Right, 2 into 3, you square it, minus 4 by 3 plus 5. What is 3 squared? It's a 9. 2 by 9, 18 minus 12 plus 5. Right, and in the end, then what then do we have? So you have 18 plus 5. And 18 plus 5 is exactly what? Okay, let's start by saying 18 minus 12. Right, we get a 6. A 6 plus 5 is 11. Aha, this is good news. Because f of minus 1 is 11, f of 3 is 11, and that means f of minus 1 is actually equal to f of 3. Okay, so yeah, this is awesome because f of A is equal to f of B. So these are the 3 hypotheses that are satisfied. Then you can find the number C, right? Then find all numbers C that satisfy the conclusion of Rolle's theorem. What is the conclusion of Rolle's theorem? Okay, right. The conclusion is that there is a number C in AB such that the derivative of the function equals 0 at C. Okay, we awesome. We happy. Right, so we take the derivative of this function. F of x is exactly this one, 2x squared minus 4x plus 5, and therefore its derivative is exactly 4x minus 4. Okay, we awesome. And now, because we have found the derivative, we shall find f prime of c, which is 4c minus 4, and this must be 0. Okay, now we're excited because we are thrilled. We can see that here the derivative of the function f at c is identically 0. So we awesome, we happy. So that 4c is 4 divided by 4, both left and right, equals 1. So now we ask ourselves the question, is this number C in the open interval? Because the conclusion is that then there is a number C in the open interval AB such that f prime of C equals 0. So we check here. And this means that the 1, okay, so we can write it properly and say, this means that this implies that at this point, C equals 1 is a member of the open. Okay, they've given a closed, but now you know that these must be open. And clearly the number 1 is between minus 1 and 3. We can look at that on the number line and say, here is minus 1, here is 3, here is the number line. And therefore the number 1 is sitting there. So there it is sitting there. Right, and this is our number C between minus 1 and 3. And then we're good. Right, so this theorem, what do we call this theorem? This theorem is a theorem very important when it comes to graphs and functions called Rolle's theorem. Now, we're going to take some time to practice the next problem on what we call Rolle's theorem, and we shall obviously now move on to the next problem, and the next problem is problem number what? Right, it's problem number 10. Right, let's do number 10. Okay, let us do number 11. Doesn't matter. Do number 11. And then now, if I do number 11, I'm leaving this one as a homework. I want to just do a trigonometric function, just for a change. Right, okay, let us start with number 11 because it's this one here is a Hayes work and this one here is your Hayes work. And we try 11 and then we shall see. I mean, these are homeworks, we shall do them obviously at some point. Now, let us look at Rolle's theorem. Now, what kind of a function is this? It's a trigonometric function. So what are the 3 hypotheses? Condition 1, continuity. F is continuous as a trigonometric function. Right, so F is continuous. Right, so F is continuous. It's continuous on the closed interval pi over 2 radians, 3 pi over 2 radians. Condition number 1 of Rolle's theorem. What is condition number 2 of our theorem, Rolle's theorem? Right, differentiability. F is differentiable. Why? Right, so f is differentiable. Right, so this one is actually f is continuous as y equals the sine of x over 2 becomes a continuous function there. This one is differentiable on the pi over 2 radians, 3 pi over 2 radians, because the derivatives of this exist. There's no way the derivative of the of sine as f of x equals the sine of x over 2. This one is differentiable because the derivatives, if you find derivative of sine, it's cosine. Derivative of cosine is minus sine, etc. So there's no way these, but it's differentiable on the open interval. Right, so take a look at that one. So it must be open for differentiability. Okay, we're good. What is the third condition? The third condition is we need to check. So we're going to evaluate f of pi over 2. Sine of pi over 2, 1/2. Sine of pi over 4. And therefore, this is 1 over the square root of 2. 3 pi over 2, the sine of 3 pi over 2, 1/2. Okay, I mean, remember from school that, let's just remind each other, you have pi over 4 radians, and then you have pi over 4 radians, the square root of 2, 1, 1. Okay, so this one here becomes the thing, becomes our special triangle for the 45 degrees. Pi over 4, then we have the square root of 2, 1, 1. Okay, now, if we come to this, and we say pi over 4 is like opposite over hypotenuse, so it's exactly 1 over the square root of 2. But I know that your calculator will give you square root of 2 out of 2 there. Okay, now this one here is 3 pi by 1 is actually the sine of 3 pi divided by 2 by 2 gives us a 4. Okay, now this is awesome news, and therefore in which quadrant is 3 pi over 4? Okay, now this one is 0, this one is pi over 2. In the middle is pi over 4, like 45 degrees between 0 and 90 degrees. But also here, because this pi over 2 is like 90 degrees, and this one is like 45 degrees, okay? So now if you have 45 degrees plus 45 degrees, so it's pi over 4, another pi over 4, it's 2 pi over 4. Then here you're going to have exactly 3 pi over 4. 3 pi out of 4. Right, if it is then 3 pi out of 4, what then are we able to achieve here? 3 pi out of 4, what then are we able to achieve at this point? We're able to achieve the fact that we have the following. Okay, the sign is positive here, and so if you even do this and you put, imagine this angle as a pi over 4 radians, right? So you have a triangle that is like so. Right, a triangle that's just like so. Square root of 2, 1, 1, this, pi out of 4 radians, pi out of 4 radians. Okay, you have this kind of a setup. And with that in mind, we're excited because there's something you can see that we can use our old friend from school and say we have SOHCAHTOA. Right, so the sign is opposite of hypotenuse, and opposite of hypotenuse is opposite. Opposite pi over 4 is 1. Hypotenuse is a square root of 2, so it's exactly this. Okay, now we're just actually covering this theorem here so that you can understand it. We stated, okay, so we stated the two hypotheses. What is the third one? What is the third one? The third one is f at this point multiplied to f at that. F at pi over 2, we can see it is 1 over the square root of 2, or it is square root of 2 out of 2, and this is exactly that. So which means f at pi over 2 is actually equal to f at what? F at pi over 2 is f at 3 pi over 2. There it is. 3 pi out of 2, like so. Now, with this stated, we are excited because we know that the three hypotheses of Rolle's theorem hold true. Continuity, differentiability, the equality. So Rolle's theorem says, hang on, if these three conditions hold true, we can find f prime of c. All right, so that the result is not. Right, so what is this? We find the derivative of the sine. Derivative of the sine. Okay, we have to spend a bit more time on the trigonometric functions, the derivatives, and so on. Okay, so the derivative of the sine becomes the cosine of x over 2. We use our old friend called the chain. We use what we call the chain rule. What does the chain rule say to us? It says that at this point, the derivative of the sine is the cosine, and the derivative of x over 2 equals what? The derivative of x over 2 is 1/2. Chain rule. And the result must be 0. Mr. Examiner, we accept. We are delighted to then say this is f prime of x. Please take note of that. It's f prime of x, so that at this point we find the next thing, which is f prime of c, and this is 1/2 the cosine of c out of 2, giving us a 0. Okay, yeah, we need to solve for c. We need to solve for c. Let us solve for c together. Let us solve for c just right now together, given this particular equation. What is the value of c? Okay, at this point, if you have 1/2 of cosine c over 2 equals 0, it means that cosine c over 2 is 0, like so. And therefore, what is this? What is this? Also, in which quadrant is this? In which quadrant is this? Okay, so remember, this is like x here. X is between pi over 2 and 3 pi over 2. Right, so in mathematics, pi over 2 sits here, 3 pi over 2 sits there. So if you say pi over 2 and that, we are here. We're here. And that describes two quadrants, the second and the third. So, which means that c over 2 equals what? 0. And arc that is pi over 2. All right. So, which means c is pi. C equals pi. So now we have c equals pi. Now, is pi there? Yes. 0, pi over 2, 3 pi over 2. Pi sits here. Between pi over 2 and 3 pi over 2, there's a pi there. There's pi there. In other words, in this question, we then say c equals pi, and this is a member, it's an element of pi over 2, 3 pi over 2. Check it out. Okay, so yeah, that becomes sort of the result. What have we done here? What have we done here? What are all these things? We're supposed to first discuss the fact that this function satisfies the three hypotheses of Rolle's theorem. Continuity, differentiability, f is continuous as the trigonometric sine function is continuous everywhere, and f is differentiable on the open interval, continuity is over a closed interval, and also, moreover, we have the third condition that says f at a equals f at b, so f at pi over 2 equals f at 3 pi over 2. So this function here is such that it is equal at the endpoints of the closed interval. There it is. Okay. Then if these three conditions hold true, then we can find our c. Our c is pi, and pi, it's the intermediate angle between exactly the pi over 2 and exactly 3 pi out of 2. We're good. So now we continue. We've done this one. We've done that one. So there's something we call a Haysberg, homework, home activity, homework. We shall get back to this if time allows, but I want us to see other topics as well. I don't want us to only know Rolle's and the mean value theorem. No, we need to know more than this. We need to know more than this. So let us try other sections. I've organized other sections even honest, talking to you right now. What now we ask this question: what does f primed say about f? What does the derivative of the function f say about the function? Because we can use a derivative to understand the function f in terms of whether the function is increasing or decreasing. Let's look at increasing and decreasing test. Increasing or decreasing test. If f primed of x is positive on an interval, then f is increasing on that interval. So if the derivative is positive on an interval, it means f is increasing. So increasing goes with what? Increasing goes with the positivity of the derivative. If the derivative is positive, bigger than 0, then it means we have an increasing function on that interval. What happens if the derivative is negative? F prime of x is negative, less than 0 on an interval, then f is decreasing. So we are effectively saying here, now, if ever the first derivative is negative, less than 0 on an interval, then f is decreasing on that interval. Take a look at figure 1. The couple of things we're able to see here, right? Here is a graph of a function f, and this function is from a to b to c to d. Okay, awesome. Now, this function here needs careful analysis. What are we able to observe? Here, there are these red lines here that indicate that the first derivative has a tangent. It is actually the gradient of a tangent that is positive. Positive is because it's upslope. Because it is going upslope, then we say the function itself is what? It's increasing. So yeah, if you could, you can draw like this. Just the tangent touches at one point, another one touches at another point. So effectively, these tangents, all of them will demonstrate that f primed is positive. Also, f primed is positive. So yeah, it is positive there because it's upslope. And then here, a tangent drawn here is going to be negative. Negative. Okay. What are we saying here with this graph? What exactly are we trying to explain here? We're effectively saying we can use what does f say about, what does f prime to say about f? We are effectively saying if ever the derivative is positive, then the function is increasing. Derivative is negative, then the function is decreasing. We're good. Okay, let's look at some examples here, because we have seen just the fact that a positive gradient means we have an increasing function, and a negative gradient implies that we have a decreasing function. What more can we say? Right, let's look at the first example on the graphs. Find where the function f of x, which equals 3x to the 4th power minus 4x cubed minus 12 x squared plus 5 is increasing and where it is decreasing. We want to check, we want to find where this function is increasing or decreasing. Okay, I know that is an easy part, but obviously we shall look at curve sketching today. Right, so we start by differentiating f. What is the derivative of f? We agree that the derivative of 3x to the 4th power is 12x cubed. The derivative of minus 4x cubed is minus 12x squared. The derivative of minus 12x squared is minus 24x. We factor out 12x because 12x is a common factor. We can factorize this to that. I know very well that we are yet to look at some problems, but factorization is pretty straightforward. To use the increasing derivative test or the decreasing derivative test, we have to know where the first derivative is positive and where the first derivative is negative. To solve these inequalities, we first find the derivative and equate it to 0. Okay, so this is our strategy. We say we first find the first derivative and equate it to 0, and when you equate this derivative to 0, we're able to see that indeed here x is going to be 0, x is going to be 2 there, and x is going to be exactly -1. At the 3 critical points, this is what we have. These are the critical numbers of f. We call them critical numbers of the function, and they divide the domain into 4 intervals. See the number line in figure 2. Right, they divide the domain. What is the domain? The domain is a set of the x values. It is such that you have part 1, part 2, part 3, and the fourth part of the domain, and the domain is subdivided into 4 parts or 4 intervals. We've seen the number line. Within each interval, the derivative must be always positive or always negative. This is very important. Always. Very strong claim here, and it's always true, fortunately enough, so we don't need to check all the time. Always. So in an interval here between -1 and -infinity, for example, we can say it is either positive always or always negative. We're good. We can determine which is the case for each interval from the signs of the 3 factors. From the signs of these 3 factors, namely the factor 12x, right? The factor 12x, the factor x minus 2, and the factor x plus 1. We're good, as shown the following chart. All right, so we shall actually show a chart. There's a chart that we're going to discuss just now about this function. Okay, right. A plus sign indicates that the given expression is positive. Okay, so we're going to use a plus. We're going to use a plus sign that indicates that the expression is what? Is positive. And a minus sign indicates that it is negative. If there's a minus sign, then indicates that the expression is negative. The last column of the chart gives the conclusion based on the increasing derivative test. For example, let's check here what we have, because we're saying the last column of the chart gives the conclusion based on these increasing derivative tests. Let's take a look. This is the chart. Right, a couple of things remain very, very important. We recall that f prime of x equals 12x. Right, we wrote exactly 12x. X minus 2, x plus 1. We explore. Right, x minus 2, x plus 1. Okay, we're good. What then do we have? In this chart here, we put the factors. Here is 12x. Here is x minus 2, and here is x plus 1. And here we put the entire, the whole part, the whole f prime of x, and here it is, and we're going to put the signs there. Right, so we take note of the fact that f prime of x is negative for x between 0 and 2 exclusive. Between 0 and 2 exclusive. Okay, so the intervals are here. The intervals are here. I know very well that there are many presentations of these, but this is the actual recommended presentation from the Stewart textbook. Okay, from the Stewart textbook, this is the presentation of the signs that we use for the chart. Right, so the interval now, we have a couple of things. So we have seen here the number line of the thing, the number line, and that shows the numbers. Like we're able to see -1, -1 comes from here. We're able to see x equals 2 comes from there. We're able to see exactly, so we start with the negative numbers, and then we have -1, and then we have a 0. Right, a 0 and then a 2. Right, we have a 0 and a 2. Take a look. -1, 0, 2. -1, 0, 2. This is it. -1, 0, 2. So we have them in order on the number line. So obviously we take this part of the number line where we then say x is less than -1. This part, which is exactly this one. And then we're going to consider another part, -1, that. Between -1 and 0, we have this one. There's another part here between 0 and 2. X is between 0 and 2, which is exactly this part. And there's another part, x bigger than 2, x bigger than 2. Right. It's exactly that part. Take a look at what we're getting here. And, okay, we have all the parts. How many? There are 4 parts. Okay, we call them intervals. Right, so we can say, Mr. Examiner, There are actually 4 intervals. There are 4 intervals of interest. Right. There are 1, 2, 3, and the 4th one. Okay, we're good. So, yeah, the first, the second, the third, and the 4th interval. We're good. Now, with these intervals here, we've taken them from the number line, and then we put the factors. 12x, we put x minus 2, we put x plus 1, we put f prime, and then we write the conclusion there. Okay, we're good. The graph of f is shown in figure 3 and confirms the information in the chart. Let us first go through the information in the chart. Right, so if we then say we are looking at 12x, whenever x is less than minus 1, right, x less than minus 1, like here, you can put an arbitrary number like any number that's less than minus 1, like minus 2, you put it in the place of x here. 12 times minus 2 is a minus 24, which is negative. Right, you put minus 2 here, minus 2 minus 2 is a minus 4, which is negative. You put minus 2 in the place of x, minus 2 plus 1, it's negative. That is why we have the negatives there. But the number choice depends on the student. If you have whatever number you choose, it will always be the same sign for all the students to choose the correct numbers in the interval that's chosen. Okay, good. What is then f primed? F primed is going to be obtained by f primed of x. The sign of f primed of x, you multiply this by that by that. In this case, for instance, it's going to be the sign of 12x, which is a negative. The sign of x minus 2 is a negative. The sign of x plus 1 is also a negative. Multiplying all these 3 things here, we get exactly negative, because negative by negative is a plus, multiplied by negative is a negative. Hence, this guy is correct. Right, so f itself right now, the function. So we are using f primed to understand the function f. So how does the function f behave? We have seen that according to the increasing decreasing theorem, if ever the derivative f primed is negative, is less than 0, we know that the function is decreasing on that interval. This interval starts from minus 1 and less. So it means that it is from minus 1 to minus infinity. We're good. Let us try also this one between minus 1 and 0. Right, so between minus 1 and 0, we're seeing the same thing. Right, between minus 1 and 0, take a number that between them, like maybe minus 1/2. You put there, it's minus. You put there, it's minus. You put there, it's plus. And then now when you multiply negative by negative, okay, you multiply this by that by that. You multiply 12x, x minus 2, x plus 1, multiply them, you get a plus. Because it's plus, then it's increasing. Increasing between minus 1 and 0. Increasing. The rest is clear. But we take note of the fact that it's going to therefore be decreasing between whenever x is less than minus 1. Right, so here's the graph. Okay, this graph has been drawn using a graphing calculator computer. But you note that here is minus 1, 0, and then they say 2, for example. Okay, this is 3. And if this is 3, then you can put a 1 here and a 2. It's okay, like that. Right, so if this is exactly true, what then are we able to see? Whenever x is less than minus 1, so we are looking at this part here, we're able to see therefore that this function itself is what? Is decreasing. So in other words, when we move towards the right, we can see the function is going down, so the function is decreasing there. Right, between minus infinity and 1. Between minus 1 and 0, we can see the function is increasing. Between minus 1 and 0, the function is doing what? It is increasing. It is going up. Right, between 0, x equals 0, and 2, what is the function doing? It's decreasing. It is going down. Yes. From here, it is going down, 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 decreasing. And also now, when you look at the part, x bigger than 2, x is 2 here, x bigger than 2, it's doing what? It is going up. It is an increasing function. Okay, over these intervals, take a look and pay attention. It is decreasing, increasing over open interval. Why are they open? They open because we know very well that at the extreme points, like at 2 exactly, the function is stationary. Right, so we know very well that the function is what? Is actually a stationary function. So these become what they call stationary points, which are our critical points. Let us move on and examine the next problem. Okay, now the theory we've learned so far is not very enough. We need like more theory. We need to gather more knowledge. We are cruising until 1/2 past, remember? So suppose that C is the critical number of a continuous function f. We suppose that C is the critical number of a continuous function f. Right. First derivative test. If f prime changes from positive to negative at C, then f has a local maximum at C. Okay? If f prime changes from positive, is bigger than 0 here, is less than 0 here, it changes from positive to negative, then we say f has a local max. So we have a local max. If f changes from negative to positive at C, negative, less than 0, positive, bigger than 0 at C, then f has a local minimum. So this, you can see, this is sort of the lowest possible point, and we say we have a local minimum point. If f is positive to the left and right of C, or negative to the left and right of C, then f has no local max or minimum at C. Right, so there is this one here. You're able to see that at this point, f prime is actually positive here, and it is actually positive there. So if f is positive to the left and right of C, here is the number C. Right, you can see that the f prime is positive to the left, but also to the right is positive. Right, right. So in other words, if f is positive to the left and right of C, or negative to the left and right of C, it is negative to the left and right of C, and we then say f has no local maximum or minimum at C. At this point, there's no local max or minimum, and we actually will then say, okay, no maximum or minimum at C. No maximum or minimum at C. Right, because it is positive all the way. Positive to the left, positive to the right, negative to the left, negative to the right. Because of this, we are able to make the determination that this function f here we're investigating has no maximum or minimum at C, has no maximum or minimum at C. So the maximum and minimum occur when the derivative changes sign from positive to negative or from negative to positive. This is called the first derivative test. The first derivative test allows us to determine if we have a local maximum or a local minimum at a point C here on our graph. We investigate further and look at how we use this first derivative test to solve problems in calculus on graphs. Let's take a look. Let's take a look at this particular example here. It's a very cool example. Find the local minimum and maximum values of the function f in example 1. Find the local minimum and maximum values of the function f in example 1. We are able to make the following determination here. We are able to make the following determination here. From the chart, in the solution to example 1, okay, there's an example we just went through together, but remember, want to find the local and maximum values of the function f in example 1. But we know that the function f in example 1 is written like this. What is the function f? Okay, the function f is this one, which is exactly 3x to the 4th power, 3x to the 4th power, and all that. Right, so we write it down. We write it down. We write it down, 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 down. Down. Okay, right. I just want to, we're gonna analyze these together just exactly right now. We're gonna, okay, we remember this one, remember? All right, we just did it, but we're gonna use it in the next case because the examiner is making reference to this, and they're saying, yeah, let's go back to this example. And now, right, from the chart in example 1, okay, let us obviously consider the chart as well, but we shall look at the function, which is exactly 3x to the 4th power minus 4x cubed minus 12x squared plus 5. which means f prime of x is equal to 12x, x minus 2, x plus 1. So from the chart in the solution to example 1, okay, I want us to bring, okay, we remember the chart. Listen, okay, we remember the chart. Okay, these are the two functions. The function f and its derivative. Okay, the derivative has already been factorized. But remember the chart we're just looking at. Where is the chart? This is the chart. Okay, let's see what the examiner is saying here. Right, we see that f prime of x changes from negative to positive at minus 1. Okay, let's check this one. Right, so at minus 1, you can see that it changes from negative slope to positive slope. Right, and this happens at minus 1. All right, negative slope, positive slope, there's a change in the slope. Okay, good. So f at minus 1 equals 0 is a local minimum. The graph is doing this, and therefore we are at minus 1, at x equal to minus 1, and then we have a local minimum. Next, right, by the first derivative test. Similarly, let's check another part of the graph here. So if you check, right, so we're able to see that for example, where else? At 0, positive then negative. Right, so similar, f prime of x changes from negative to positive at 2. Right, as noted previously, f of 0 equals 5 is a local maximum value because f prime changes from positive to negative at 0. Yeah, so in other words, at 0 you have this, at x equal to 0, the function changes from positive to negative, so we have f prime is positive, f prime is negative, and therefore because of this, then we have a local max. Okay, and then now if you look at the f prime changes from negative to positive at 2, let's check what is happening at 2. Right, at 2 you can see it changes from negative slope to positive slope. It changes from negative slope to positive slope. Right, I want us to look at it in many ways. Okay, you can even look at it from the chart, because you're able to see that if ever you have minus 2, so you have to the left of minus 2 to the right of minus 2, and therefore you can see there's a change from negative to positive there, from negative to positive on the chart. So you're able to see, therefore, that at 2, there is most certainly a sign change in the derivative. Right, so if it is actually obvious that 2 from negative to positive, right, from negative to positive, so the graph is sort of like this, from negative to positive, and therefore the function has what? Has a local minimum there. Right, so at x equals 2, we have a local. We have a local minimum. The graph is like this. We have f prime of x is negative, changes from negative to positive. And then f primed is positive. F primed is negative. F prime is positive. Okay, y'all. We are then saying at x equal to minus 1, we have a local minimum. Local maximum at x equal to 0, local minimum at x equals 2. These are our critical points. We call them 0, 2, minus 1, and we've classified all of them. Right, so in terms of which one is the local max, in terms of which one is the local minimum, etc. We continue. Let us look at another example. Right, in the next example, we focus on example 3. Find the local max and minimum values of the function. So let us look at the next function, which is the g of x function. G of x is equal to x plus 2 sine x, where x lies between 0 and 2 pi. As in example 1, we start by finding the critical numbers. The derivative is the following. The derivative of x, we know is 1. The derivative of the sine is the cosine. So g prime of x equals 0 when cosine x equals minus 1/2. So yeah, we actually make this equal to 0, and solving for what we are actually attempting to solve for x. So from this particular equation, we achieve that cosine x equals to minus 1/2. The solutions of this equation are right. So if you say cosine x equals to minus 1/2, we're able to see therefore that the actual solutions are 2 pi over 3 and also 4 pi over 3. So we actually are saying the cosine function is negative. We used the cast diagram. And when is it negative? It is negative in a couple of quadrants, the cosine in this and that, in the second and the third. And now we have 2 pi over 3. 2 pi over 3 is like, because pi over 3 radians is like 60 degrees. So this one is going to be like 120 degrees. But also we have an interesting thing. We have the 4 pi over 3, which is like 4 times 60. And 4 times 60 is like 240 degrees. Right, 240 degrees sits here. And this is like exactly, so this is 120 degrees, which is exactly 2 pi of 3. And this one is 4 pi of 3. And this is 240. Okay, right. We split the domain into intervals according to the critical numbers. So within each interval, G prime is either always positive or negative. Always positive or always negative. And so we analyze G in the following chart. Let's take a look at the chart. Right, to analyze this chart very well and to make sure you miss no critical points here, you miss no intervals, you consider all the intervals, we need to order these properly. Right, we have 2 pi out of 3, which is on the number line, but we also have 4 pi out of 3 on the number line. Okay, we are then saying here, we are able to see clearly that here you're going to consider the interval that is such that, because there is 0 somewhere there. Okay, the examiner was very, very restrictive. The examiner said, hang on, student, don't go to the negative angles, please. Stay between 0 and also 2 pi radians, so we are bounded here. Right, but we're going to consider, therefore, from 0 to 2 pi thirds, which is actually our first interval. From 2 pi over 3 to 4 pi over 3, it's our second interval, the first, the second. And then we actually going to consider the third one. So we have 1, 2, 3 intervals between 4 pi out of 3 and 2 pi. We're good. Right, let's look at the derivatives and the slopes of this particular function, g prime of x. Right, so if we have actually here g prime of x is this, we perform substitutions. Okay, right, so if we put 2 pi over 3 in the place of x here, you like put 120 degrees in the second quadrant. We know very well, according to the cast diagram, the cosine is negative in the second quadrant, so that this is going to be negative. So cosine of 120 is like exactly minus 1/2. Okay, you can check that. You're going to go back and revise y is minus 1/2. Okay, that is from school. But you multiply 2 times minus 1/2. You get a minus exactly 1 there. Right, okay, right. I want us to do this with much caution. Let us, okay, so we take an angle that is in the middle here. Let's take an angle that sits in the middle. Right, but we exclude the extremes. Okay, so an angle in the middle is going to be, you take this one, you divide by 2. Right, so if you divide this by 2, or you take half of this is going to be like pi out of 3. Okay, pi out of 3, which is half of these intervals, so pi out of 3 sitting in the middle. Right, pi out of 3 is like, pi out of 3 sits here and it's like 60 degrees. Okay, let's do cosine 60, 1/2. Okay, 1/2 plus by 2, 1. 1 plus 1, 2. Positive. Positive there. So the positive is correct. Because it's positive, then it's increasing over this interval from 0 to 2 pi out of 3. Between 2 pi out of 3 and 4 pi out of 3 exclusive, we take the middle. What is the center number? You take this, you add this to that, you divide by 2. Right, so when you do that, when you add this to that, what do you get? You add 4 pi to 2 pi to 4 pi, you get what? You get exactly 6 pi. 2 plus 4 is 6 pi out of 3. And this becomes 2 pi. But you add these things and divide by 2, you get exactly pi. When you get a pi, you put it in the place of the cosine here for this. So cosine pi becomes exactly -1. And now 2 times -1 is a -2. 1 minus 2, it's a -1. It's a negative. So it means it's decreasing from 2 pi thirds to 4 pi thirds. Okay, we continue without ceasing. Right, next, between 4 pi of 3 and 2 pi, what do? We add these two guys and divide by 2. In the same way, we're going to get a positive, meaning it is increasing there. Positive means increasing. Okay, we have seen these, but we need to find the local max, local mean. What is actually happening here right now? You can see that a 2 pi over 3, it changes from positive to negative. Looking at the chart, at 4 pi over 3, there is actually a change from negative to positive. We're good. Right, because G prime changes from positive to negative at 2 pi over 3, the first derivative test. Okay, yes, we said that. G prime changes from positive to negative at 2 pi over 3. So at 2 pi over 3, the change from positive to negative. So the first derivative test tells us there is a local maximum at 2 pi over 3, and a local maximum value is this. So there is a local maximum, and then we put it in the function g, which is exactly the function g of x, which is x plus 2 sine x. X plus 2 sine x is the function g. So yeah, 2 sine x. Okay, so we substitute the 2 pi of 3 and we get this number here, which means this number here is the as said already, because it changes from positive to negative, then it means that you have a local maximum, local max. Okay, likewise, G prime changes from negative to positive at 4 pi over 3. We saw that at 4 pi over 3 it changes from negative to positive. At 4 pi over 3 changes from negative to positive. Because of that, then it changes from negative to positive. All right, because of that, and so this one is the number. So we have a local minimum. Local minimum. The graph of G in figure 5 supports our conclusion. Let's take a look at the graph here. Right, so let me see if I included that particular graph. I think I did not. Okay, right. But now what you're able to see at this point is that in the end, then you'd have the local maximum that occurs at the change from positive to negative, which is x equals 2 pi of 3, and also x equals 4 pi of 3. Okay, so it changes from negative to positive, changes from positive to negative, like so. Right, I think that this is awesome. Right, we shall continue in our next discussion about more graphs and functions, more curve sketching techniques, and obviously we shall discuss more because I'm just looking at the time. We started at 16:30. What time did we start? We started at 16:30. We're supposed to stop at 17:30. Right, good. So any question there, Atlahong?
No.
Okay, that's fine. So we're recording this. I'm gonna send you the recording. You can try some of the things we discussed. We can check on WhatsApp. You can alert us. You can send a message and tell us what else you'd like us to what you would like to see in our next meeting. Okay.
Okay.
Okay. Thanks, Atahang. It was awesome having a discussion with you. We shall see you again. As usual, normally our meetings have to be like Friday and Saturday. So yeah, our plan is to see you on Friday. Okay. Yeah, thank you so much. Until next time, we shall send the recording in the next couple of minutes. Take care and enjoy evening. And goodbye.
Okay. Thank you very much. Bye.
Goodbye, Tlehong.